Welcome to Oregon State Mathematics Department Applied and Computational Math Seminar that is today going to be part of the Women in Data Science event that is taking place at Stanford University. Thank you for being here. We have a pleasure to introduce the speaker for this event today, Sarah Emerson from the Department of Statistics. She came here from Harvard University where she had a postdoc. Prior to that, she received her PhD from Stanford in statistics. But prior to that, she received her bachelor's degree in mathematics, also from Stanford. So welcome to Sarah, and she will be talking to us about, I won't read the whole title, but matrix decompositions. Thank you.
Thank you. Thank you so much for the invitation. And I am pleased to be here talking to you all. So I'll be talking about, in particular, sparse methods for clustering, and I'll explain what I mean by that. So I'll go through some background, brief overview of clustering for those of you who might not have had a lot of experience with the problem, and then talk about some proposed approaches that involve applying a penalty to select variables to use for the clustering. And then another idea for producing the sparse clustering that is fairly simple but outperforms these penalized approaches in most cases, and we'll look at some comparisons to demonstrate that. So motivating example, and this could be data of your choice, but in many of the papers where this was discussed, the motivating example was microarray data, but any data where you have a matrix where the way I'm going to set this matrix up, each row corresponds to a different subject, so a different person, and each column is, we'll say, an expression level for a different gene. So we have P different genes, in this case 20, and we have 12 different subjects here. We'll be dealing with bigger problems, but just so you can visualize it. And the goal is to discover a grouping of subjects who have similar gene expression patterns. But our challenge is that most genes are probably very similar across all the subjects. So there are only a few genes that will actually determine the clustering. And our job is to simultaneously identify which genes matter and identify the clustering. So in this case, I generated this data so I know which genes matter. And I realize that red is a challenging color if you are colorblind, but that is unfortunately the highlighting color that I have used. So the bold-faced red columns here are the genes that actually matter for determining the grouping of these subjects. So if I put those 6 genes together, we start to see the grouping emerge. And then if I reorganize my subjects, it's a little bit more clear. So that is our challenge. So before we get to how to identify the variables and the groupings, let's first discuss some background on clustering. And there are a plethora of clustering algorithms that have been proposed over the years. In fact, so many that at one point somebody suggested that every time you propose a clustering algorithm, you have to knock 2 others out of the literature. So there's a ton. We're going to focus on 2 basic types, and each of these 2 types have a number of variants as well. I'm going to talk about k-means clustering, where you have to specify, so you have to tell your algorithm how many groups you're looking for, and then you find the best division into those k groups to optimize within cluster similarity, and that means minimize the within cluster distance between points and maximize the between cluster distance between points. The other type of clustering we'll be talking about is what's called hierarchical clustering. So hierarchical clustering is a collection of methods where you produce a nested set of clusters by recursively dividing your data collection into 2 groups, so it's a binary division process, or you can do it in a bottom-up unit, and we're going to be looking at that. So you start with your whole set of data points, each in their own cluster, and you recursively merge clusters until you have everything in the same group. Okay, so just a little bit of notation background. Again, we are considering observations on p variables obtained for n different observation units. So each unit is a p-dimensional vector, and I'm going to let boldface xi denote the vector for the ith data unit, and then boldface x is our data matrix. And again, my goal is to group the rows into several clusters that have similar values on these measured variables. And most, but certainly not all clustering algorithms, we really don't need the raw data. What we need is a distance matrix that tells me how far two different observations are from each other. So I want to know what is the distance between observation x1 and observation x2, for instance. So we would need an n by n distance or dissimilarity matrix. So we construct a distance matrix where the ij entry indicates how dissimilar objects I and j are. And this doesn't need to be a true distance. It's just a dissimilarity matrix. So it can fail some of the requirements for a distance. It need not satisfy the triangle inequality, for instance. You could choose an infinite number of distances here. What we're going to focus on today is Euclidean distance, or squared Euclidean distance. So L2 without taking the square root. This choice of Euclidean distance is not totally necessary for what we're going to do, but it does make the approach that I'm going to consider a little bit more natural. It's also one of the most commonly used, at least initial distances when people are trying to construct clustering, but there are a number of others that people also consider. Okay, so k-means clustering, we said we have to specify the number of groups, so we have to specify what k is. And then there are a few different algorithms that are used for k-means clustering, but the basic idea is you obtain an iterative solution by first partitioning the data into k different groups, and then you calculate the centroids, means in this case, of each of those groups, and then you reassign your observations to the centroid that they are closest to in the distance metric that you've chosen. And then you calculate the centroids again, reassign, calculate again, reassign until you don't change, so until your solution stabilizes. So as a quick illustration, this is my data in 2 dimensions, so I just have observations on variable x1 and variable x2. My data points are these colored dots, and right now the colors are just totally randomly assigned. And then I have chosen 4 completely random points to be these centroids. So my first step is just randomly assigning centroids. Then I assign each data point to the centroid that it's closest to, move the centroid to the middle of its assigned cloud, and repeat that process until the centroids stop moving. So in that final round, the centroids don't move anymore. So this is the solution that I have obtained for this 4-means clustering on that data. Now note that the final clustering result that I get will depend on the random starting configuration. So in general, it's not considered a great idea to just start with one random configuration. It's recommended to run this with multiple starting configurations and then choose the clustering that is the best out of all of the different final solutions you get to. And best can be measured in a few different ways, but one fairly standard approach is to choose the clustering that maximizes the between cluster sum of squares. And so this is basically like an ANOVA concept. So we are wanting to maximize the pairwise distance between observations that are in different clusters, and likewise minimize pairwise distance between observations that are assigned to the same cluster. So this expression here is expressing the between cluster sum of squares in terms of the total sum of squares, which is this first term, and the within clusters sum of squares, which is the second term. This is going to come up later, which is the only reason I'm making you look at this formula. So as we're trying to come up with a sparse solution, we're going to be looking at the between cluster sum of squares with a slight modification. Okay, hierarchical clustering. As we mentioned, there are multiple ways to obtain a hierarchical clustering of a data set. The method that we're going to be considering is a bottom-up hierarchical clustering. And what you get at the end is a nested set of clusters, and you can display in a tree or dendrogram. So a dendrogram is a branching plot that indicates how similar different observations and different groups are. So groups that are merged down low are very similar. The labels here are not important. All you're really meant to be looking at are the branchings of these trees. So these 2 observations are very similar to each other. These 2 observations are pretty different from these 3 observations because they don't merge until way up here. And I have 3 different dendrograms here because there are multiple ways of choosing when I have 2 different groups. How do I decide how close 2 groups are to each other? So how should I decide that group A is merged with group B instead of being merged with group C? And that's what this linkage, which is displayed in these 3 different plots, determines. Okay, so agglomerative hierarchical clustering, meaning bottom up, what we do is we start with each observation in its own group, and then we merge the 2 most similar groups to be a single group. And then we recursively continue that process until everything's in one group. So what we have to define is how similar groups are. And there are, again, many ways we could choose to do that, but the 3 most common ways to do this are complete linkage, where the distance between 2 groups is the distance between the most distant objects in those groups. So it's the maximum pairwise distance between elements in group A and elements in group B. We could also consider what's called average linkage. So the distance between group A and group B is the average pairwise distance between an element in A and an element in B. And finally, single linkage is the minimum. So it's the closest point in A to the closest point in B. And so depending on which of these ways of defining similarity between groups we choose, we get different clusterings. And here's just a quick illustration of how that can differ. So I'm going to go through the mergings for this same data set for the 3 different linkages. So they make the same choice in the first step, which is to merge those 2 points. Then they merge those 2. So far, we're getting the same clustering. But now we've gotten a difference. So the single linkage chooses to merge those 2 clusters together, whereas average and complete stick that 1 point onto the leftmost cluster. So notice that these 3 dendrograms have different branching patterns. They are dendrograms based on the same data set, but they look different because of the linkage metric that we have chosen. And then what we can do once we have a hierarchical clustering dendrogram is we can decide how many clusters we would like to investigate. And to obtain our desired number of clusters, we just cut the tree so that it makes that many groups. So here is what I would get if I cut the tree to get 2 groups for each of these 3 different dendrograms. Or I could cut it to get 3 groups or 4 groups and so on. So I can, with a dendrogram, I can, after the fact, choose how many groups I want, and I can just cut the dendrogram to obtain that many groups. Okay, so that's clustering, but all of those clustering methods have been obtained using our dissimilarity matrix, which was computed on our entire collection of variables. But our problem is that perhaps only a few of our p variables matter. So in gene expression data, for instance, perhaps only a few genes differ significantly between the different groups of subjects. And the remaining genes are just noise. They're not contributing any signal to our solution. And that noise can be a problem. If we perform our clustering using all p of the variables, then the signal from our few informative variables can be overwhelmed by those vast number of noise variables. Even when all of our variables are relevant, it is often possible to find a subset of the variables that gives us almost as good information as the complete set. And that can also be a worthy goal if you're dealing with massive data and you have issues with data storage capabilities or data collection costs. So our goal in either case, either when only a few variables matter or when we just need to do a data reduction to manage costs and storage, our goal is to identify a subset of these p variables that can be used to obtain a good clustering of our observations. So here's an example where I have 500 variables measured on 60 different observational units. So the rows, again, are my observations. I've labeled them as subjects. And the columns are my variables. And this is a heat map, color map, of the value for each subject at each variable. And you're not meant to see a lot here. But what I'm going to tell you is that I simulated this data with 50 variables that actually contain a clustering signal. And the point here is that that's not remotely obvious when you look at this matrix. If I isolate the 50 variables that matter, you start to see the clustering. It's still not super obvious. So let me pull off the noise and just show you the signal. So this is the signal. I have 3 clusters, one of size 20, one of size 10, and one of size 30. And my job is to start with this original matrix, identify those 50 variables that matter, and therefore identify that clustering into 3 groups. So here's what happens if I perform a k-means clustering using all 500 variables, so the 50 signal variables plus the 450 noise variables. The confusion matrix that I get is this matrix on top. And the way I've labeled this, the true class label doesn't really mean anything. So all we're really looking at is, are the observations that truly belong to cluster 1 all assigned together? And they are for cluster 1, but for cluster 2, they're split between 2 different clusters, and for cluster 3, they're split between 2 different clusters. So the clustering that I'm getting is not recreating the true grouping very well. In contrast, if I cluster using only those relevant 50 variables that have the signal, I have perfectly preserved my clustering grouping. Even though my labeling is changed, the labeling doesn't matter. It's just the observations that were in cluster 1, these 20, are still in the same cluster with each other. And the observations that were in cluster 2 are still in the same cluster with each other. Likewise, we can look at a similar problem using a hierarchical clustering approach. So again, here's my starting data matrix. There are 100 observations, so 100 rows, and 1,000 variables. And of these 1,000 variables, 250 variables contain a signal that divides these observations into 5 groups. And again, there is nothing I'm expecting you to see here. But if I isolate the 250 variables that matter, you start to see the signal along their diagonal blocks along this line. And then if I pull out the noise, you can see what the underlying signal is. So again, if I cluster these data using all 1,000 variables, the hierarchical clustering that I get is this top plot. And I have colored each leaf in this dendrogram. So each of these final lines is one observation. I've colored each leaf by the group that it is truly assigned to. And what you see is that my groups are wildly mixed up in the dendrogram that we get if we use all 1,000 variables. However, if I use only the 250 variables that actually contain signal, I recreate this grouping perfectly. So if I were to split this dendrogram into 5 clusters, those 5 clusters would exactly capture the 5 clusters that I generated the data with. Not terribly surprising, right? Noise hinders our signal ability detecting ability. Okay, so that's our problem. And there are a number of approaches that have been proposed to try to find the signal variables that matter and produce the clustering. Among these, and this is certainly not an exhaustive list, but some of the more prominent approaches, at least in the statistical literature, are a model-based clustering algorithm. There's some penalized approaches, including penalized log likelihood. So we specify a normal distribution-based likelihood for the clusters and then maximize that likelihood with some penalties. We can cluster based on just the first principal component of the data. And then there's this approach, sparse k-means, which came out 2010, but then has been added on to in the past couple years. So these are the k-means approaches that are kind of float up to the top, but there are a number of others. There are also a few hierarchical clustering approaches that are, again, attempting to simultaneously find the variables that matter and also produce the clustering. And again, I'm going to be focusing on the sparse k-means and the sparse hierarchical clustering of Witten and Tibshirani because they demonstrated in their initial paper that the algorithms they proposed do a better job at variable selection and cluster construction in a number of the settings that they considered, actually in all of the settings that they considered, although you can't consider the exhaustive set of circumstances. So I'm going to compare a new approach to these methods. So let's first explore what these methods do. So both of these are penalized methods, meaning that they are optimizing some criterion subject to some penalties. And so here's the criterion that they are optimizing. What they are doing is assigning weights to each of the different variables. So each gene gets a different weighting. And we're going to call that weight W sub L for the Lth gene. And then what they are trying to do is maximize the weighted between cluster sum of squares. So each variable contributes differently to this between cluster sum of squares that we're trying to optimize. But we have some constraints on these weights. First of all, we constrain the L2 norm of the weight vector to be less than or equal to 1. That's mainly just an identifiability constraint. This next constraint is the one that's most important. We are constraining the L1 norm of the weight vector. So if I add up the absolute value of all of the weights, the sum of those absolute values is constrained to be less than some tuning variable s. And we are going to look into what value of s's should we choose and how does s affect our solution. And then finally, all of the weights are positive, which means this absolute value here is a little bit redundant. But it's this parameter s that really helps us identify the variables that we're going to be using. So here I have, for our k-means example, where we had 500 variables, 50 of which matter, and I've made the 50 signal variables the first 50. And what I'm going to show you is a series of plots as I change that tuning parameter s, so this red constraint here. As I increase the value of s, we'll look at the weights that are assigned to our different variables. So when s is 1.1, we see that this variable here gets a weight of almost 1. And then we have a couple variables with weight above 0. But the vast majority of our variables get a weight of 0, meaning they're not contributing at all to our clustering solution. As we increase s, these weights start to come out of that 0 line, and we get more and more variables entering our problem. And finally, as s gets up toward the square root of p, so square root of 500, all of the variables eventually enter our solution. Same idea for sparse hierarchical clustering. So again, we're going to assign weights to the different variables. So WL is the weight for the lth variable. And then what we're basically doing is we're assigning weights to maximize the distance on the lth variable times uij, where uij is essentially you can think of as a weighted singular vector element. So what this is intuitively doing is it's sort of looking for a weighted reconstruction of the matrix that just uses a few of the variables to best reconstruct the whole matrix. And again, the same constraints are applied to these weights. So we have an L2 norm constraint just for identifiability. We have an L1 constraint. This is what gives us the sparsity in our solution. And then a positivity constraint. So these constraints, and in particular the L1 constraint, induces sparsity in the variables. Most of our weights are going to be set to 0, which means that variable, the corresponding variable, is not going to matter. So it won't be used as we construct the clustering that we're going to be building. A touted benefit of this approach is that variable selection is therefore automatic. So only variables that have a non-zero weight are selected for use in our clustering algorithm. The number of variables that we end up including is determined by this tuning parameter s. So as we saw, if we relax that constraint on the L1 norm, we include more variables in our final solution, whereas if we have a really tight constraint on the L1 norm of our weight vector, we are forcing just a few of the variables to have a non-zero weight. In both k-means and hierarchical clustering, the weighting vector and the clustering solution are found through iterative optimization of the weights and the cluster assignment. So it's just a optimization problem. It's I think it's not a truly convex problem, but it depends on the penalty you apply. For this penalty, I think it actually does turn out to be a convex problem. So some challenges of this penalized approach. First of all, it's very slow due to the iterative nature of the solution, and you're having to do a fair bit of matrix inversion, at least in the hierarchical solution. The other bigger challenge is that for a given level of sparsity, the solution is generally suboptimal. So if I said, give me the best solution that just has 10 variables, the solution that this penalized approach comes up with 10 variables is not the best choice of 10 variables. It's also difficult to ask it to give you 10 variables. You set a tuning parameter value S, and it returns however many variables it wants. But there is no explicit relationship between S and the number of variables that you get out. So that will depend on the problem. It depends on how strong your signal is and how many different groups you have and so forth. So it's hard to say, I want a solution with exactly 50 variables that contribute. You have to try a wide variety of S to get the level of sparsity that you want. The final potential drawback is that the way that the variables contribute to our clustering distance is in a weighted fashion. So if we look back here, when I am clustering these variables at this value of S, what I'm saying is these variables contribute a lot towards my decision on how good the clustering is, and these variables just contribute a tiny bit. So they're not contributing in the same fashion as they were observed. They're contributing in a weighted fashion, which is not necessarily a bad thing or good thing, but it is something to keep in mind. Okay, so instead of doing this iterative penalized approach, we decided to look at what the singular value tells you about which variables matter, right? We know that a singular value decomposition is just a way of expressing a matrix as the product of an orthogonal n-dimensional matrix, and you can write it a few different ways, but I'm choosing to do it as an orthogonal n-dimensional matrix, an orthogonal p-dimensional matrix, and then a rectangular diagonal matrix D, where these are the left singular vectors. These are the elements of D are our singular values. The elements of V are our right singular vectors. And we can write matrix multiplication in a number of ways, but writing the singular value decomposition like this shows us that we're writing X as a sum of rank 1 matrices, and each rank 1 matrix has a different contribution to the final X matrix that we're adding up, and that the amount that it's contributing is represented by dj, the singular value. Note that the right singular vectors, which are the columns of this V matrix, have one entry per variable. So variables that have a large magnitude entry in the first few columns of V are likely to contain more information or structure, at least when we're considering Euclidean distance, L2 distance. Another thing to note is that if we have centered the rows, the rows of our X matrix, then the covariance matrix for our columns can be written in terms of our singular values and singular vectors like this. This is going to be relevant in a moment when I talk about how to create scores for the variables. But note that the diagonal elements of our covariance matrix, that is just our marginal variance for each variable, can be expressed in terms of our singular values and our right singular vectors. And it's the square of our singular values times the square of the corresponding element of our singular vector. Okay, so again, our example, where we have 50 signal variables that matter out of a total of 500 variables, and there are 3 clusters. So what I want to show you now is what our singular vectors look like. So this is our first singular vector, so this is the first column of V. And note that the first 50 elements of that first column of V have all larger magnitude than all of the remaining elements. Not terribly surprising. We know how singular vectors work. Our second right singular vector is noise. What this is showing us is that the signal that I have put into this matrix is a one-dimensional signal, and it's contained in those first 50 variables. Again, this isn't earth-shattering news. But what this hints at is that we can use these singular vectors to capture which signal variables matter, at least when we're dealing with a squared distance. And if we look at the singular values, this is what we see. And what this is telling us is that our first collection of our V vector and our D are really capturing the majority of the signal, and the rest of what we're seeing is kind of noise that blends in with each other in a very heuristic way of expressing it. Okay, so what we can do to use that information is basically take our singular vector, our singular vectors, and add up across a certain number of them. We have to think about how many of them. But we're going to add up is what is the contribution of the jth variable, or what is the weighting of the jth variable in our first singular vector? What is the weighting of the jth variable in our second singular vector? And so on. But I'm also going to scale that by how important is that singular vector. So here we see our first singular vector is very important, drops off a lot to the second, and then kind of falls off to the end. Okay. So, yes?
Is your signal constant across the 50 variables?
Is your
Signal
constant? It is in this case, but we're going to look at examples where it's
because
not.
that would explain why you only get one significant
Absolutely.
singular vector and not 50.
We will see, well, so one challenge is even if your signal changed, if it has the same grouping, you would get so we have to think about the dimension of our clustering. And we'll see this when we look at the hierarchical clustering matrix, because then we have a 5-dimensional clustering signal instead of a 1-dimensional clustering signal. And so then we need more than a singular vector to capture it. That's why what I'm proposing is, instead of just looking at the first singular vector, for k-means clustering, we only need to look up to k-1. Because if you're looking for k groups, what that means is you have a k-1 dimensional grouping effect at most, essentially. So we can only have k different patterns that we're looking for, so we only need to look at the first k-1 singular vectors. So what I'm doing is I'm adding up the contribution of the lth variable to the first k-1 singular vectors and scaling that by how important those singular vectors are. So that's what the d value tells us. And then we use the variables that get the largest score on that scale. So in this case, I'm looking for 3 groupings, which means I only need to consider the first 2 singular vectors. Here's my first one, and as we saw, my second one was noise. These are now squared because what I really care about is the magnitude, not the direction of these elements. So what I do is I take these squared singular vector elements times the corresponding value of d plus these squared singular vector elements times the corresponding value of d to get a score for each variable. And here are those scores by variable number. And then what we do, if we want to do a clustering that just uses 10 variables, is I just draw a line and I say, give me the variables that result in the 10 highest scores. And those are the variables that I'm going to consider have the most important signal for this clustering, or 50. Here is that same matrix, but I've permuted the variable number so that it's not quite as, it doesn't quite as much look like cherry picking. But what you see is that there are a few variables that really stand out, and most of them don't get a very big score. Same idea for hierarchical clustering. The only challenge here is that in hierarchical clustering, we aren't looking for a specific number of groups, which means we don't know the dimension of the signal that we're looking for. So now we have to be a little bit more relaxed in terms of how many singular vectors we include in our score. And this is a somewhat arbitrary choice. So either the minimum of p-1, where p is the number of variables we have, or n over 4. This choice is not hugely important, but what you want is to include the number of singular values, singular vector pairs that capture your signal, and then leave everything else out. The trouble is we don't know the dimension of our signal. So going a little bit beyond makes it more certain that you will capture your signal. So this is a slightly larger number than we will need in a lot of cases that you might come up with. So again, we're going to add up the contributions of the first B singular vector, singular value pairs. So here was our hierarchical clustering example where we had 10,000 variables, 250 of which mattered with this signal. So now it's a 5-dimensional signal pattern. And again, what really matters is not what the pattern is within each of these variables, but it's the pattern in each of these groups that determines the dimension of our signal. So it's how many groups we have. Here is the score we get. And remember, this is including the first 250 singular vector, singular value pairs. So it includes a lot of noise, because I have a 5-dimensional signal, but I'm including 250 dimensions. Oh, n over 4, 25. So again, to choose the variables that we're going to use in constructing our clustering, we just take the variables with the highest resulting scores, and we just use those variables to construct the clustering. So now we want to compare this approach to variable selection to the sparse hierarchical clustering and sparse k-means clustering. So we have to think about what are the criteria that we use to compare clustering methods. And there are 2 criteria that I'm going to focus on. The first is the number of relevant features that are correctly identified. So in our examples, we had 50 relevant features in the k-means example and 250 relevant features in the hierarchical clustering example. And the question is, am I correctly selecting features from those sets? The second, and perhaps more important metric that we'll be looking at is the classification error rate, which is just looking at, for all different pairs of observations, xi and xj, how many times are xi and xj in the same cluster for the assigned clustering but not in truth, or how many times are they in the same cluster in truth but not in the assigned. So it's how many times the clusterings disagree with each other across all the pairs of observations. So a higher classification error rate is worse, right? High error is bad. Okay, so for k-means, we've seen this example. Just a little more background on how I generated this. The signal that I generated had a magnitude of 0.8 relative to a standard Gaussian noise background, so signal to noise ratio of about 0.8. And I ran, just because of space on slides, 6 simulations. We've run a lot more. But just to show you, I generated a new data set 6 times with those same parameters and looked at across a range of different tuning parameters. Remember, the tuning parameter S determines how sparse the solution is in the sparse k-means method. And then once I got a solution using sparse k-means, say it came up with 10 variables that had non-zero weight, I found the top 10 variables according to just the singular value weighting and compared a solution with the same degree of sparsity. So here what we have are, for those 6 data sets, on the x-axis is how many variables are included in the solution. So this is how many variables had a non-zero weight. And on the y-axis is the classification error rate. So lower is better. The red data points are the solutions using just the singular value decomposition variable selection approach. And on the y-axis is the solution we get using the penalized k-means approach. And the only point of this slide is that we are fairly uniformly below them, quite substantially in many cases. So for the same degree of sparsity, the solution we are finding has a dramatically lower classification error rate. Of further interest are the running times, and these running times, the actual times don't mean anything, but it's just the order of magnitude difference between them. This was run on a slow laptop, so 83 seconds probably would take 3 seconds on a good server. But 83 seconds relative to 4 seconds. It's a significant improvement in running time speed. All right, for hierarchical clustering, I looked at a signal that had magnitude 1 relative to a background standard Gaussian noise. So again, signal to noise ratio of 1 in this case. This is the same matrix we've been looking at with 250 variables that actually matter. And I'm going to show you 10 different simulated data sets and the resulting dendrogram. And again, I used the proposed sparse clustering algorithm to produce a clustering, and then I matched the number of variables that that clustering used so that we're comparing across the same level of sparsity. And I somewhat optimize the tuning parameter S to try and get the best classification error rate. So I'm trying to give them a head start here. That I'll talk about in a moment, how S is chosen. But what I'm showing you here are the colored dendrograms. What we hope to see are leaves of the same color largely together. And in most of these cases, we are seeing that more using the singular value variable selection approach. To summarize that in a more quantitative manner, here I have all of these 10 simulations listed. The number of variables that were selected in that simulation is in this top row, so 348, 347. Remember that there are a true 250 variables. So we're selecting a few more variables than we really need. The classification error rate using the penalized approach is in the second row, so 0.14, 0.24. Remember, higher is worse. We are consistently getting a lower classification error rate, in some cases dramatically. And then we look at how many of the variables that were selected were actually among the signal variables. Using the penalized approach, 168 out of these 348 variables were actually among those signal variables that mattered. In contrast, when we select 348 variables, we're getting 194. And you see across the board, we are getting more of the signal variables just using a simple SVD approach as compared to using a penalized approach. So lower classification error, more of the variables we're selecting are actually the relevant variables. So, conclusion is, at least when we're dealing with Euclidean distance, just using a basic singular value approach to finding variables seems to do better both in terms of identifying the variables that matter and giving you reproducing the clustering that actually generated the data. Partly this is because the lasso penalty is not really what we're wanting to optimize here. We want to say, give me the 20 best variables that produce a clustering that maximizes some criterion, and that's not exactly what the lasso criterion does. Nor is it a natural criterion for the sparse matrix decomposition that this penalized clustering approach is based on. So that was an earlier paper where they were just proposing a sparse principal components and sparse singular value decomposition. So the issue is the lasso penalty does induce sparsity, but it doesn't induce sparsity in a way that maximizes the criterion that we most care about. One of the challenges with the lasso is this reweighting of the variables, which may or may not be desirable, but it's not something you get to choose. Now, one thing people have looked at in using lasso for variable selection is to use this weighting just to select the variables, but then use the variables that were selected and go back and use them in an unweighted fashion. In some cases, that does tend to do a little better. So instead of using the weights that the lasso is enforcing, throw those weights away after you've chosen the variables. The other issue with the lasso and L1 penalty in general is that the way that variables are added to the model, they creep in. So the first time a variable is added to the model, it has a really minuscule weight, just above 0. So unless you get your penalty just right, you're not getting the optimal solution with a given level of sparsity, right? There are a lot of solutions that have 15 variables, and they have different weightings. So that 15th variable that came in, what we really probably want is when that 15th variable is at its peak right before the 16th variable comes in. That would be the best 15 variable solution, but that's a very hard thing to tune for using the lasso penalty, right? We would have to search a very fine grid of S values. An open question is, how many variables should we include? Remember, I did the hierarchical clustering tuned to end up with somewhere on the order of 350 variables when the true signal was 250 variables. That's a difficult question in any context, but we can answer it to the same extent as, or better than, a penalized approach. And most of these answers rely on an approach like cross-validation. So we set aside some of our data, like leave out half the observations. We fit our model, come up with our scores for the 50 observations that we didn't leave out, and then we look at, if I maintain 20 variables, how well do I recreate the data for the data that I held out? So it's basically looking at some measure of prediction error on held out data. And you choose the number of variables that gives you the best prediction error for your held out data. We can also kind of look at these score plots, at least using the SVD method, to see if there's a clear breakpoint. So there's a cloud of variables that get a score way up here, and then there's a pretty substantial break. That's only going to happen if your signal is pretty sharp. And in most real data cases, there is no clear break, and you kind of just have to draw a line somewhere. Another way that this is often done is just to say, 50 is a nice round number, let's keep 50. That's obviously not a super objective metric, but it can be a useful way to ballpark comparisons. So that's all I had for you. Any questions?
We have a few minutes for questions. Okay. Let me go first. Weights. You said you were using an optimization algorithm to do it. How does that scale? So let's say,
Poorly. Yeah. So are you meaning particularly for these penalized approaches?
Yeah.
It scales very poorly. So I think it's order of the number of iterations required is kind of the fuzzy element there. But I think these computations are order of like NP squared, and then how tight you want your solution to be can dramatically blow that up. So.
And the data you're using, this is data that you generated,
Yeah,
right?
these are just simulated.
Have you, I'm assuming you have applied this to some data that came from somewhere else to see how that would work on?
Yeah, we've applied it to some, well, in the original sparse clustering paper, they'd applied it to some breast cancer data to group patients into different phenotypes. We can do that. I always push back a little bit on because this is a common thing in statistics journals to require that you apply your approach to real data to show that it works. And my response is that's a single data set where we don't know the truth. So what are we learning by applying it to this? We can see that we get a different solution, and that's informative, but we don't know if our different solution is better or worse. If it's the same solution, then I can't say a lot. But yeah, it runs the same as long as you have a data matrix. We've tried it on much bigger examples. They're just harder to display on a screen, and take a while, especially for the sparse algorithms.
Okay. Thank you. I think we're going to thank Sarah again, and thank you very much.